welcome everybody to the latest episode of our COMET Webinar series. We're delighted to have Dr. Evgenia Ilyinskaya as a speaker today. Evgenia is a University Academic Fellow at the University of Leeds and part of the COMET team. She's also involved in international research projects such as Airborne, European volcanological research collaboration. Evgenia is an expert in volcanic emissions of gases and aerosols, which is studied at volcanoes around the world, and will today present us a research about how these emissions can affect the environment and health. And yeah, we're very eager to hear more about this research.
Hi everyone, and thank you for coming and listening in. So like Daniel introduced me, I specialize in what volcanoes emit into the atmosphere, and not ash, but gases and aerosols, and how that impacts the atmosphere, air quality, environment, and eventually health. And this kind of video shows actually quite well what we are interested in. I often, when I give public talks, I ask people to point out what they think the hazard is. And people, quite rightly, point at those spectacular lava flows. And of course, they're very dangerous. And in this particular eruption in Hawaii last year, it destroyed a lot of homes. But in addition to that, there's something maybe slightly less visually obvious, but nevertheless, something that can be quite dangerous as well. And that's sort of that kind of brown or sometimes bluish smoke that's coming off the lava flows and going up into the air, and that's volcanic gas and aerosol cloud. And I'm very lucky to have a great number of actually fantastic collaborators from across the world. Here at Leeds, I have a PhD student called Rachel, and in Cambridge, another PhD student called Emily, Penny, and Marie and Anya Schmidt. I know you might remember, she was here at Leeds before. Emilio at UCL, and at Oxford, Tamsin Maven. And in addition to those just a few names we mentioned there are many more collaborators to whom I'm very grateful. And we also work a lot with non-academic partners such as Icelandic Met Office, Hawaii Department of Health, Hawaii Volcano Observatory, and also the Volcano Observatory in Nicaragua in Central America. Excuse me, I might have to cough these times. So in addition to kind of human collaborators, these are the kind of my volcano collaborators that we will talk about today. So a few years ago, there was a big eruption, a lava eruption in Iceland called Plume, and we did some interesting work on there, so I'm going to introduce that today. And then just last year, we traveled to Hawaii. This was a big eruption that happened there, and it was very similar to the one in Iceland. In fact, in many ways, they're sister eruptions. But this one opened up in the middle of a residential area and burned something like 700 homes. And then we have also been working in Central America at a volcano called Nicaragua, called Masaya, which isn't producing those spectacular eruptions, typically speaking, but it has been degassing, emitting those polluting species for decades. And actually, it sometimes takes breaks, but then it starts up again. And as long as there are written records back in the 16th century, Masaya has been doing this. And going a little bit further back in time, it's almost impossible to talk about volcanic impacts on the environment without talking about the Laki eruption, which happened in Iceland just over 200 years ago. It was a big eruption, looked very similar to the eruptions I showed you in Iceland and Hawaii, but about 10 times larger. And it had impacts across at least the northern hemisphere, if not there. So just to go a little bit back to the basics, what do we mean when we talk about air pollution? What is air pollution? Air pollution is a big umbrella word, but it can contain some gases which are bad for us because they can cause various respiratory problems such as asthma. And in volcanoes, we find a lot of sulfur dioxide gas, which is called SO2 for short. And that gas is particularly nasty to people with asthma because it can induce asthma attacks, deadly asthma attacks, even at very low levels. So some volcanoes which receive a lot of visitors. They have installed warning systems so that people can be evacuated when the gas concentrations go up in the little. And in addition to the gases, we also have aerosol particles or particles. And if you have followed any kind of air quality alerts, you might have seen those reports talking about things like PM 2.5 or PM 10. And that that basically tells us how big those particles are. PM 2.5 particles are all particles smaller than 2.5 microns, and they're so small. You can see, in fact, comparison there between the size of PM 2.5 and human hair. You can see how tiny they are. So if you breathe them in, you imagine they can get past their sort of all your natural barriers and penetrate deep into your lungs or potentially even further. And we know there's a correlation between concentrations of small particles and negative health impacts. And that's why padded particle microns keep saying size matters. And there are many different sources of air pollution. So just a few to mention there: wildfires, desert dust storms, volcanoes, and of course human-made emissions. And air pollution is something we should be concerned with and should be researching, because WHO, World Health Organization, estimates that over 4 million deaths occur worldwide as a result of exposure to air pollution. And most of those occur in developing global south countries. While we think we understand pretty well that size of particles is important to health impacts, we know a bit less about what the composition of those particles means in terms of impact. I mean, we know all probably instinctively that on those 4 photographs that the particles emitted by those pollutants will have different composition. But actually, we know still very little about how that translates into impacts. What we do know, so people hopefully remember their periodic tables, those elements, and a lot of them we know to have negative impacts. For example, if a lot of them accumulate in the water we drink or in the food we eat. And it so happens that volcanoes, they're kind of recycling stations of the earth, and they emit almost every naturally occurring element. And of course, they also emit a lot of those elements highlighted there as pollutants. And what can those elements do? Well, in small concentrations, some of them are actually necessary for us. Like fluorine, F on the periodic table, is actually necessary for our teeth and is in fact added to our toothpaste. But drink or eat too much of it and your teeth will start to degrade. And that photograph is taken in an area near a volcano. That volcano produced a lot of fluorine, which goes into their water, and people have teeth problems. But how do actually volcanoes compare to anthropogenic human emissions? Should we be worried about them? Should we even bother considering them? Well, yes, actually, they are quite a significant source. So this graph shows 2 recent eruptions, one in Iceland, one in Hawaii, compared in terms of how much sulfur dioxide they emit compared to European Union countries all put together, and China, which, as we all know, probably is a big, big emitter, still burning a lot of coal. And you can see the numbers are quite striking, especially considering that the eruptions they emit as point source, while countries, they of course split up their emissions between their factories and their cities, etc. And occasionally we have even bigger events, like Laki eruption in the 18th century in Iceland, which produced approximately 10 times more than those recent eruptions in China. And while those kind of eruption sizes are not that frequent, they're still not uncommon either. So, for example, Iceland produced eruption like that approximately every 200 years. So the question is, are we expecting another one of those of that size? In addition to sulfur dioxide, I must say that sulfur dioxide has been a focus of most studies on volcanic emissions and impacts. But what we're discovering more and more recently is that volcanoes emit a lot of other stuff in addition to sulfur dioxide that is important for environmental and health impacts. So this graph shows a few selected pollutants, which are referred to by environmental agency and health agency as metal pollutants. Although strictly speaking, for the chemists among us, they're not all technically metals, but okay, we'll refer to them as metal pollutants because that's what the agencies talk about. So the graph there shows several selected volcanoes and several countries. So volcanoes are colored, and the countries are on black and white scale. So what we can see there is some of them, let's start over at selenium. Volcanoes are a very significant source, and they can actually rival some of the largest emitting countries like China and exceed some of the European countries. And this is just one eruption and emitting as a point source. And once those pollutants are emitted, they go up in the air and they're transported with a prevailing wind direction in what we call volcanic plumes. I just want to introduce that word because I'm going to be using that in now. What we have been seeing is that, of course, those large emissions at source, they must go somewhere. And if we look at populated areas downwind of the volcano, we can see that air quality isn't what it should be without an eruption going on. So this is some data we collected last year in Hawaii. The colored bars are populated areas at different distances downwind of the volcano. So the green one is 80 kilometers downwind, the light blue is 160 kilometers, and the dark blue is 200 something kilometers. And then that's compared to large cities in the mainland US. And again, we see that for some of these pollutants, actually the kind of the rural area on an island in the middle of nowhere has higher concentrations than large cities. So that's true in this case for selenium, copper in some cases, arsenic is pretty comparable, aluminium, iron, manganese. Lead and zinc, they're actually a lot lower, and that's because they come mostly from anthropogenic emissions, so dirty fuel. And in fact, if you compare Hawaii during the eruption last year compared to 20 years ago when there wasn't such an eruption going on, the levels of those two pollutants have decreased because people are using generally cleaner fuel. So that's good news. If we go back to that very large eruption in Iceland in the 18th century, unfortunately we don't have any direct measurements of what impact that might have had. As you saw, we do know something about how much sulfur dioxide emitted because we can look at the rocks that were formed during the eruption and make some estimates about how much gas was released into the atmosphere. But there are no records of impacts either in Iceland or further afield. But people did keep records, people wrote diaries, there were newspapers published, so there is some evidence of what might have been going on. So all this data is mostly just from records that people took. And their records exist from what this red circle shows there, so covering most of the northern hemisphere, and they mention something that is undoubtedly linked to the eruption. So in Europe, people describe this as a dry fog, and crops were failing across Europe, even though this eruption happened mostly during the summer. So I once had a fun project of looking at newspapers published in 1783 in the library and looking for what people might have written in newspapers at the time. So this is a letter from Copenhagen that was published in London newspapers in August 1783. And they say, for some time past, we have had excessive hot weather and the sky is constantly covered with a thick fog, which without totally intercepting the sun, deprives us of its brightness. Far from moistening the ground, this fog dries up the grass in the fields and the leaves which drop off the trees, most of which are now left bare. And remember, this is in August, so it's pretty strange that some leaves and grass are drying up. And there have been some attempts to look at whether there's any association with mortality with this large eruption in Iceland. And it's very hard to untangle what people died from back 200 years ago because diagnosis and medical records are not particularly good. So I'll show you some evidence, but it has to be taken with a little bit of a pinch of salt. So the solid bar there shows, the dashed line shows average mortality for time periods around 1780. So that as you go through the year. So there's a high generally in the winter and low in the summer, as is to be expected and as it is still today. And then the solid line is the year of the eruption. So during the year of the eruption, you have a unseasonal peak during the summer, where in fact average mortality should be at its lowest, but there you have a peak. And then also the winter peak appears to be higher than average. So whether that's linked to the eruption, just a coincidence, is still not quite certain, but certainly there is some evidence. And in the newspapers, there are also several records that something was potentially going on in the health department. For example, this one says, the season for months past has not been healthy. The bills of mortality have increased prodigiously, and by the register of the parish on St. Anne's Circle, it appears that 186 persons have died there in the months of September. So, how do we explain this? What happens to the emissions in the atmosphere? Why do they spread so far and cause so much damage, as it seems? So here's a little bit of a kind of some words and some science that we use. This is a cartoon demonstrating the eruption in Hawaii last year. So, but it's typical for most eruptions. So because remember, these eruptions, they produce mostly lava and gas. They don't explode in an ash-rich cloud that goes up into the stratosphere, like Pinatubo or Mount St. Helens or something like that. So they do have some thermal updraft, but very quickly, relatively speaking, they reach neutral buoyancy, and then they transport it downwind with whichever prevailing direction the wind is blowing in. And as the plume travels, it has background air being mixed in continuously, and you have chemical processes going on all the time. So one of the best known reactions is conversion of sulfur dioxide gas into sulfuric particles as it's oxidized. So more oxygen is added to the sulfur dioxide, and it goes from being gas to being an aerosol. And nowadays, that dispersion of sulfur can be monitored. So most air quality stations around the world can pick it up, and also can be forecast by dispersion models. So of course, this would have been nice to have during the lucky eruption in 1783, but we won't put it there. There are two examples there of real-time forecasts that were being given out during those gas-rich eruptions in Iceland on the left and Hawaii on the right. However, in spite of, we've come quite far with monitoring and forecasting sulfur, there are still some things we're still discovering. And the eruption in Iceland 5 years ago, that was a really good opportunity for scientists and kind of operational agency to improve their methods. So, for example, one of the things that our group discovered was that the pollution may potentially go on for longer than previously thought, and the forecasting model accounted for. So what we saw that was happening was that this young, very sulfur dioxide rich plume was leaving Iceland and kind of drifting towards Europe. And then about 3 days later, it had turned, like swirled around Europe and then come back as a chemically matured cloud. And why was this important? Well, it wasn't forecast at the time. So, for example, this is just one day during the eruption when this is the official forecast. And it was telling us that the plume is going north, the air quality in the capital city here in the southwest is going to be good. But people are noticing that there was something going on. There was something not quite agreeing with good air quality. Because this is just one quote, but there was a big sort of citizen science database where people could record what they were feeling. Excuse me. So this guy was saying, this day was very remarkable, eyes and throat were burning. And of course, the reason for that was that the plume had gone to Europe and then come back, but that wasn't accounted for in their forecasting models. Okay, we want to see, I mean, okay, maybe eyes and throat were burning, but you know, maybe it wasn't really that serious. So we looked at health registers in Iceland, and we looked at, in particular, asthma medication dispensation, visits to the GP, and hospital emergency room visits. And we only looked at the days when kind of the air quality forecast was saying the air quality from volcanoes should be good, but in fact that kind of old European travel plume had come back to Iceland. So, so what we found, I appreciate you might not be familiar with plots like this. This is commonly used in public health studies, but essentially anything that's above that horizontal red line means an increase from average from before the eruption in those particular health outcomes. So you can see that the data points, they are above the red line for asthma medication, for GP visits, and for the hospital emergency room visits. And we split the results by age group, and the under 18s, so children, were the most impacted ones, which is quite common with air pollution impacts anyway. And in Iceland, it's quite common practice to have children and toddlers sleep outside in prams. This picture is taken during the eruption in the winter. And of course, when people knew from the forecast that the air quality was going to be bad, they kept their children indoors. But that kind of European returning plume that wasn't forecast, people didn't know about it. People put their kids outside. So we think it's important to be able to forecast the plume a bit better. So moving on a little bit further, so I've just talked about how we can forecast and how we can monitor sulfur dioxide in real time. But in comparison, we know extremely little what happens to the other pollutants. Remember, there's metals like selenium, copper, zinc, lead, etc. Actually, I could count with like one hand how many studies there have been that looked at what happens to those things when they're emitted from volcanoes. And most studies don't go further than 5 or 10 kilometers away from the volcano. So do they, for example, in the case of Iceland, reach Europe? Do they even reach the other side of the island in Hawaii? We don't know. It's been kind of assumed they follow the same dispersion pattern as sulfur, but nobody had checked. So that's one of the things we decided to do when the eruption started in Hawaii last year. We wanted to track the dispersion of not just sulfur, but all of those weird and wonderful pollutants quite far away from the volcano. This eruption, as I mentioned before, it opened up in a residential area called the Leilani Estates, and this moving diagram shows the extension of the lava flows during the 3 months of the eruption. They produced, as I mentioned, quite devastating effects. But in addition to that, if you remember, it was emitting as much sulfur dioxide as the whole of China, just from that one little hole in the Leilani Estates. So it looks quite spectacular. So you can see houses there for scale at the bottom. And you can visually see the air pollution around the islands. So on the left is the highest peak in Hawaii. This is not the volcano that was erupting. It's a completely separate mountain. It's over 4,000 meters high. And you can see that haze that is not coming from above, it's coming from the ground up and sort of bathing the mountain. And that's the pollution from the volcano. And on the right was when we visited 1 year later, when the eruption had stopped. And the contrast in air quality was absolutely fantastic. And near source, it was also quite a visually, you could see the impact. So on the left, the dead vegetation and the cloudy skies. This is not clouds like meteorological clouds. This is air pollution from the volcano. And this is actually the nastiest fieldwork conditions I've ever been in. I've been close to volcanoes before, But there it was just unbelievable. It was raining complete acid, and the clothes had to be thrown out after that day. And 1 year later, you can see it was quite fantastic. It was exactly the same spot. Vegetation had bounced back. I rode my bike there, had a great day out. So it was wonderful to see. So I probably won't go into details like how we did things. I just want to say we sampled both near source. So this is my student Rachel on the photograph on the right, on the left, sorry, flying a drone into the eruption plume. And my other PhD students here in the chemical hazard suite, collecting samples at the source. And also where those stars are showing, that's where we set up our air quality stations to capture how the emission of the pollutants is changing from source into the far field. So we co-locate our instruments often with the existing air quality stations. And again, I point out to people that this sky is not like that normally. It wasn't like this year, we went 1 year after eruption. This was on the other side of the island, and it was even there it was completely cloudy all the time. And the kind of work we do is that we collect physical samples. We don't, in this particular instance, we didn't use satellite images or remote sensing. We physically had to go and collect samples. So it's not real-time data by any stretch of imagination. It takes months and months of lab work to analyze all those strange elements. There are no real-time techniques to analyze them. And this is just very briefly, but we also worked with researchers at the University of Hawaii who are experts in simulating where volcanic plumes go. So they could help us. We could combine our direct observations with simulations and kind of produce maps for different pollutants and not just sulfur ones. So our big question was, in this spectacular plume, you can see that stuff is falling out already from the plume quite close to the vent. And the question was, does everything fall out at the same rate? Or do some pollutants stay in the plume longer than others? And do some fall out quicker than others? So this is kind of our first results plot. But the answer was no. Stuff does not stay or does not fall out at the same rate. Some stuff falls out quicker than other stuff, generally speaking. And in fact, we saw that elements which are typically listed as pollutants, they're in red, versus kind of more benign elements. We saw them falling out faster from the plume than, the pollutions were falling out faster from the plume than benign elements. So on the x-axis here, you see distance from the eruption site, and this is those lines represent how fast they're depleting. So those red polluting elements, they were depleted by up to 95% of their original mass just within the first 40 kilometers away from the volcano, while those more benign elements, they were depleting much slower. How do we explain this? It was a very interesting result, and not one we had necessarily expected, or at least nobody has ever seen it before. So we started thinking about what do we know about those elements, how do they behave inside the volcano before they erupt. And in fact, there is a sort of a continuum between those fast depleting elements and slow depleting elements. It also in the way how they behave before they erupted. So this very fast depleting element, that red group, they are something we call high volatility elements in the magma. And the blue ones are what we call low volatility elements. And I appreciate not many people might already know what that is. So I'm going to try to explain it in very simple terms. And for that, I'm going to use soda bottle example, because volcanologists absolutely love soda bottles to teach. So, for example, we love showing this to say why gas is important for producing eruptions. Because if there's no gas left in your soda bottle, no matter how much you shake it, you won't produce an eruption. But in any case, this is a slightly different YouTube video I'm going to show you to explain how volatility works. So if we imagine that our soda is magma, and we just all we do first of all is remove the the cap, immediately some things will start escaping, like carbon dioxide. Your coke will go flat after a while if you do nothing else to it other than removing the cap. So, and then we start heating it up, and more stuff will start escaping. So water will start to vaporize, and some other things as well. And that's what we mean by volatility. So stuff that escapes very, very easily is highly volatile. But towards the end, some stuff will still be there, still be in those glass balls or in our magma body, if you like. And that stuff is what we call non-volatile. And the same thing is happening in the volcano. So this is what that erupting vent of Kilauea would have looked like, more or less. You have that sort of lava body splashing up, and you have also gases volatilizing off the top of the magma. So what's becoming gas and escaping into the atmosphere, those are highly volatile elements. They can form gases, they can escape. On the other hand, that sugar cube in the Coke bottle or the non-volatile elements in our magma, they don't become airborne like gases. They can become airborne, but only when they form tiny fragments of magma. When magma kind of splashes up and breaks up into tiny pieces, and that's the only way they can become airborne, but they're not volatile as such. So to bring this back to our original question, how does that affect, stuff falling out from the volcanic plumes sooner than other stuff? Well, those volatile elements, the ones that form the gas and escape, they form different chemical compounds. They form salts of sulfates and halides. While that non-volatile stuff, that sort of tiny magnets of magma, it's essentially the same composition as ash or volcanic sand. It's a completely different composition, and it has very different water solubility. So that salts of sulfur and chloride, they are almost completely soluble in water, and the others are not. And you know this instinctively because if you put a bit of table salt in your glass of water, it will dissolve very easily. If you put a bit of sand or ash in your glass of water, it will take a very, very long time for it to dissolve. And we think this is what's happening in the plume, that more stuff that is more water soluble is scrubbed out of the very abundant water in the plume very quickly. You make the poorly volatile stuff, poorly water soluble stuff behind. And in terms of impacts, because that's what my talk is mostly focusing on, so what these results meant was that the areas nearest to the volcano are kind of disproportionately disadvantaged. Not only do they receive more of the stuff because they're closer to the volcano, but they also receive much more of the polluting stuff. And that's not something that was appreciated necessarily during the eruption. So based on our work, unfortunately this was not in real time, but afterwards. But in any case, it's very likely that an eruption will happen again in Hawaii and elsewhere. These are the kind of recommendations we made. We said, look, based on our results, sulfur dioxide dispersion is not the same as the dispersion of all the other pollutants in the plume. So pollution-specific dispersion and hazard maps may be required. In addition, because those highly polluting elements, they're very water-soluble and they fall out very fast from the plume, they're likely ending up in rain and rain catchment systems. And in that area, people actually live quite self-sustainably, and all their drinking water and sort of household water comes from rain catchment. So it's very well worth looking at whether rain quality and therefore drinking water quality was affected. And last but not the least, this volcano is very active, and although it produced a huge eruption in 2018, it has in fact been degassing for the past 35 years. So it might very well be that pollutants have accumulated over time in quite large quantities in different areas. And then the last volcano I want to go to is in Central America, in Nicaragua, and we have been working there in a very fun project because, I say fun because it includes not just volcanologists, but also social scientists, artists, historians, medics, and the local communities. It was funded by GCRF, a project called Unrest. And people live very, very close to this volcano because it's not erupting explosively. It's not really erupting in the sense that we think about eruptions, like lava or ash coming out. It's just pumping out gas and aerosols year in and year out. It's been doing this for centuries. So, but because it's not exploding or erupting lavas, people actually live quite close to it. The closest community is within 2 kilometers. So those people have been impacted, have been living there, potentially breathing in the volcanic emissions for their whole lives. So we were quite interested in going there and asking people what is it like for them to live there. And we made a short documentary, and I'm just going to show you the first minutes of it, but it's available on YouTube if you want to watch it further. And essentially, it's people telling us in their own words what is it like for them to live there. It's in Spanish, but there's English subtitles.
Yo vine aquí de Chichicuay. Aquí compramos este lugar que no se ha hecho.
Estamos en la comunidad Panamá Amadores, una comunidad que es bastante afectada por los gases volcánicos. Tengo de vivir aquí 17 años. En esos 17 años pueden tener experiencia de cómo el volcán nos afecta, cuáles son los puntos que tenemos que tener, cuál es lo que tenemos que hacer, ¿verdad? En estos tiempos de lluvia, que sabemos que cuando va a ser colota de humo.
So this is some of the things that people have told us about. Metal, for example, rusts in a matter of days, and we've seen this with our instruments as well. So both, not just outdoors, but indoors as well. So any kind of metal objects inside their homes get to this state just in a few days. So that means that people have had to adapt to it, and they had to, for example, learn to build their houses entirely without nails. But this introduces a somewhat complicated problem, is that traditionally people would cook indoors using firewood, which of course is a huge source of indoor pollution as well in many countries, and that is a huge sort of premature killer. And people have been encouraged more and more to move to using gas, which is a clean cooking fuel source. But this is a gas hob that's only 2 months old, and it's rusted to bits. So how do you solve this problem? And then there's the agricultural side of things as well. So most plants cannot survive the acid rain and the conditions near the volcano. And in particular, coffee, which is Nicaragua's largest export product, is particularly sensitive. And you can see here, this is during a period of low emissions, but nevertheless, you can see the sort of acid burn on the leaves. And when the gas really picks up, then the coffee growth can be absolutely decimated. And in fact, the Nicaraguan government has been very concerned over the years. They've not been particularly concerned about people, it seems, looking at historical records. There are no mentions of impact on health. Actually, there is one document which mentions impact on health that says there's absolutely no problem for people to be working and living on the volcano and doing the coffee. I mean, we know that's not true, so why do they bother mentioning it? Maybe not to scare people away or something like that. But they have been very concerned with impact on coffee. So they have actually introduced several schemes to try to battle the volcano. In the 1920s, they came up with a scheme where they were going to build a funnel below the volcano and siphon off the gas. And in fact, not just like move the gas to somewhere else, so where it wouldn't damage the coffee, they're actually going to collect it and sell it commercially. And this failed very dramatically. And then there's been several attempts to bomb the volcano to kind of close off the vent. And in fact, they requested that a nuclear bomb would be dropped on the volcano. And of course, that would have had much worse consequences than the volcano does. But it didn't happen. But they did drop not a nuclear bomb, but sort of a normal bomb, so to speak. And it didn't do anything to the volcano either. On the other hand, we've also been asking the local communities, how do you cope with this? What, have you learned anything that helps you deal with your everyday life? Well, actually what we learned is that farmers, just local farmers, they found some types of fruits that are native to the volcano and therefore very well adapted to growing on the volcano. So these include dragon fruit and pineapple. I'm not sure that's actually native, but it grows very well on the volcano. In fact, farmers tell us that the pineapples grow better on the volcano than away from it. So because those plants were already sort of adapted to growing on the volcano, it meant it didn't take any effort to make them grow. And it sort of kick-started in the 70s a booming local export business of those fruits. So it's actually kind of interesting to compare those fantastic government schemes, which often include consulting foreign experts that have never been to the area and producing this sci-fi plan to siphon off the gas or something, versus actually those, if you like, non-engineered local methods that have actually proved to be much more effective. And this is my last slide. So what I hope to show today is that volcanic emissions, not just when they produce ash, but when they're kind of just pumping out a bit of gas, a bit of aerosol, can have very widespread and very long-lasting emissions. And they can have an impact that has to be dealt with, but often simple solutions to a long-term problem are much more effective than over-engineered solutions. And but kind of involving local communities is always the key, is what we learned, at least in Nicaragua. So thank you very much.
Thank you very much, Evgenia, for this fantastic talk. We have time for questions, both locally but also from the remote view.
So I have to repeat the question so that people online can hear it. The question is, how do such eruptions compare to eruptions like Tambora in terms of size?
Well, in terms of the effects, normalized for the size.
Yeah, I see. In terms of effect normalized to the size. Yeah, very good question. So the main thing that makes the impacts different is that Tambora style eruptions, they're very powerful when they happen in terms of just like throwing stuff up into the air. So they go above the troposphere and into the stratosphere. And I don't know what your background is, so I hope I'm not. So basically, in the stratosphere, all the weather happens in the lower layers of the atmosphere, in the troposphere. In the stratosphere, there's no rain, so there's nothing to bring those pollutions down to Earth. So they stay up there much, much longer. So one eruption, even if it just lasts a day, the pollutions can stay up in there for years, 2 to 3 years, typically speaking. So they don't impact air quality as such because they're too high up. We are much lower down. We are impacted by emissions that happen at ground level. On the other hand, if stuff reaches the stratosphere, it can block out incoming sunlight and can impact global climate. So those are the main differences between large explosive eruptions and these guys.
I have one question. If the 1783 Lucky eruption occurred today in the same scale, what, in terms of gases and aerosols, what would be the largest impacts on society?
Yeah, so, okay, so I don't know, do you want to Should I repeat the question?
Or maybe
Yeah. So the question is, if likely eruption would happen today, what would the likely impact be? Yeah. I'm sorry, I have to speak away from you. Yeah. So there have been some studies. I would say not enough, but there have been some to kind of look at the impact of a modern day eruption of the size of likely. So actually, Anya Schmidt, who used to be at Leeds, she did a lot of work on this. Of course, people have better healthcare, so that's a good thing, but there are also more people. And it was estimated that just the increase in the aerosol pollution during the eruption would increase the spike in mortality up to 10%. That was the result of that particular study. Yeah, so it's not something to be taken lightly. And in fact, a few years ago, such a likely particular eruption scenario was included in the UK National Risk Register, which includes all sorts of things from terrorist attacks to flooding and and this volcanic eruption as well, just to be better prepared, just so that all agencies that might have to deal with it know what it is when it happens, and they within the organizations they might think up what do they need to do if it does happen. I'm just imagining here, but like let's say a health service would be like, okay, we're going to need to increase the available asthma medication by X million %. Okay, we know about it. We can be more or less ready.